I feel better today. So let's continue like this. But okay too? So, I am always ready for simulation. And you? It's big fun. So actually, when we do a simulation work, we did yesterday, it's important to verify many things. Actually, we didn't do one thing. So now we will look into that one. And that was the anisotropy, the texture, with respect to the testing, what we want to do on it. So there was a little bit of small problem with our simulation yesterday, not serious, but let's look into what kind of initial texture we had in the material. So, for this purpose, I don't know if you know this beautiful software which is called ATEX. I'm opening it. ATEX is actually, well, as you can see, powered by Vandenberghe and Beausire. They are both colleagues in my laboratory in maths, younger colleagues. One of them was my PhD student, like 20 years ago almost. Well, he very well understood simulations and textures and so on. So together with another colleague who is also a texture man since long time, they made this software which is called ATEX for doing texture presentations, texture study, also microstructure studies, all kinds of different diffraction experiments can be examined. The results can be examined with this software. EBSD, for example, also. And even there is a simulation part in it, which can be used even for polycrystal simulation. So they were trying to make kind of something very much complete software. The software is also interesting in that it doesn't require any additional software. So this is a standalone. All what they needed in terms of mathematical packages, they integrated into the software. It's free. So if you go to the home page, which is somewhere, is it indicated? You have to go to internet and you type ATEX software. Here it is, www.atexsoftware.eu. And then you can download. I strongly suggest that you make familiar yourself with this. It's not really difficult to use. There is also a user manual and a lot of instructions. And it's also intuitive. So you can find your way. What we need here for this moment is to visualize what kind of texture we were trying to do tensile test on it. So our texture is represented with this orientation list, This is what we use, the list of orientations with 6,000 lines, and each line specifies one grain with the Euler angles. So the Euler, rotation angles in orientation space. Is the first angle is in degrees. Phi 1 angle, the second is the phi angle, and the third one is the phi 2. And the last number is the volume fraction representing the size, the volume of the grain in the polycrystal. This is a relative value. The sum of all these volumes is giving the volume of the sample. Now, in order to visualize what kind of orientation distribution these 6,000 grains are making, we are going to use here in the ATEX software the import data option, this one, import. Specifically here, orientation list, this option, you see when there is Raman spectroscopy, they included in this software. So orientation list is the option to choose, and it leads to choose the orientation list file. Well, I call it textin.smt, although it was texin.dat, but I renamed it to SMT because this is the kind of, you see in the list of extensions here, this is the kind of extension which is recognized by the software as a texture file. So I open this one, then it shows the beginning of the list so that one can be sure that, yes, this is what I want to have examine. And of course, there are many options here which are appearing, but they are all, actually, almost all of them, they are already well chosen, like here in degrees, different columns. Here you see specified Euler angles and volume, all is already in order. Phases, well, this is phase 1. Crystal structure is cubic. So the lattice parameters are 111, and the angles of the different axes are 90 degrees. It's Cartesian. The cubic reference system is Cartesian, not like the hexagonal. And then this is it. We just have to push the button, create ATEX file. And the message says that a file has been created, and we just have to open it. On the new page, it says textures, yeah, and then phase 1, sample symmetry, calculation method, and so on. There are some details which, for people who speak the language of textures, it's a very, very small population on the planet. They understand what it is. But for everybody, it is sure it's the sample symmetry is something important, right? Sample symmetry. We can use the triclinic option, or monoclinic, orthorhombic, and axisymmetric options. It is actually making, if our distribution is not symmetric as we want, and it is going to make it symmetric, okay? The triclinic option means no symmetry. Actually, there is no symmetry what we impose on the sample. And this is usually what we do. We are not imposing symmetries. Although the option is there, like orthorhombic distributions are for rolling processes. Different monoclinic symmetries, they are for shear deformations. So the process, it is here, actually, this is a sample symmetry, meaning that, you know, if you apply that symmetry, then you will still have the same properties on the material. But the best thing is not to impose, because it might be that your initial, your set of orientations, they are not at all, you know, in the right symmetry. Just see as it is now, without imposing anything. And then the other options here, calculation method, C coefficients, it says. We have individual orientations, 6,000, but we want to get some kind of continuous function, which is describing the orientation distribution. So for this purpose, these individual points, which also they have volume, they are converted into, you know, they are fitted with continuous functions. So one possibility is this C coefficients, which is spherical harmonic functions, which are used to convert the discrete distribution into a continuous one. It's quite an art, mathematical art, to do that, you know. But it's possible. And then box sizes, well, 5 degrees means that every 5 degrees we will have intensity values. And then development even and odd, these are the rank of the coefficients, because it's a series. The C coefficients is like you know, a Fourier series or like a polynomial series, but it's different. Up to 22 and 21. Very important parameter comes here, the Gaussian width. To make these continuous function, a Gaussian distribution is inserted for each orientation. That's already a continuous function. And then the sum of these is altogether fitted by these spherical harmonics. It's very complex. It started in like 1965 with the work of Heinz-Joachim Bunge, a German person who established the technique how to do this. This is a very mathematical but beautiful procedure, and it is inserted here in the software. We don't have to know too much about it, actually. The principles are good to know, but we are not supposed to program this. This is done, and very well done. So the Gaussian width, you know, it's that for one orientation, how much is going to be the, you know, the half width of the distribution? Here it says 8. It's actually 8 degrees. So for each orientation, you imagine like it's not really a single orientation, but, you know, a continuous orientation with a peak at the exact position. If we change these degrees, 8 degrees here, to smaller, then we will have more spotty representation, and as increasing this value, we will have more even. The 8 degrees is a standard choice, but it's possible to make other values, you see, like 5, even 1, whatever you want. 8 is proposed. Isotropic part, you can add isotropic texture to your texture study. Here it is, we are not doing that. And then comes, you see here, hexagonal convention. we are in cubic, so we don't even look at it, right? Textures. Here, there are 4 options. We can have pole figures. We can have inverse pole figures, IPF. We can have sections. That means sections of all the orientation distribution function, Euler space. And here comp means components. One can also look at, calculate the volume fraction of selected texture components. After, you can even rotate the texture if you want around different axes, because you might not be in the reference system where you want to be. Okay, so on the right side we see the first part of the orientation distribution, which is still discrete. And now, just pushing the button on pole figure, we will see the creation of 4 pole figures. So these distributions come, and now we can examine. So 111 pole figure, 100, 112, and 110, but one can change, adding or removing. Here you can define what kind of pole figure you want to see. 111 pole figure, for example, means that this circle here, this pole figure, is actually this, like, imagine that it's a sample surface, your sample surface, on which there is x, y, and z direction. The z is oriented perpendicular. Imagine that this is the sample reference system. It is actually. And then crystallographic direction, specific one, is selected for each grain. The 111 here means 111 direction in each grain has a specific orientation in space, and can be projected, on it's oriented like on a sphere, this direction in the physical space, and cutting a sphere at a point and then project it down on the surface. It's a projection, pole figure. So we can see the probability and the distribution of the 111 type of directions within our sample, in the sample reference system. This is very useful. One can easily visualize the meaning of these pole figures. So the 111 here, you can see that there is here in the middle a peak, and there's a second a kind of circle. It's not perfectly circle. We realize that our distribution is not perfect, but actually 6,000 grains is not enough to make it perfect. We would need 6 million, and then we would see very nice, symmetric thing. The sample symmetry is not there. We did not impose, because we really wanted to see, and that it is, how much approaching the symmetry, and how much is deviating. So there are 111 poles in the crystal. There are 2 kinds which are appearing here. There is a texture in this material. For example, the 100 directions. In the cubic elementary cell, these are, the axis directions in the crystal reference system. So they are so that in the middle there is a strong peak. This is red here. And the iso density levels here, they show you that, it's red, so it's 4 up to 4.5. The 4.5 means that it would be 1 if the distribution is random, isotropic. So 4.54 means that much times not isotropic with respect to the isotropic one. But it's relatively not too high value, but not too low either. We see these concentrated, circles. So we have a texture actually, probably the sample was a bar. A bar, it's a copper bar, which was extruded, and a circular bar, and with a circular, die, it was extruded and obtained. So this is why the sample symmetry somehow is appearing in the texture. So the z-axis, because here the z is in the middle, you see, and around this axis we see these circles. So the z-axis is a circular symmetry axis. Now to be sure which texture components are important in this texture, we can study another projection. This is look at it, projection on the sample reference system. Crystallographic directions appear in the sample reference system. The other one, we could have chosen here the IPF option, inverse Paul figure, and this kind of triangle. So when we open this one, it will be the opposite thing. Here, instead of like 1, 1, 1, it is written X. And the 1, 1, 1 is here, and 1, and so on. So now we are in the crystal reference system. And what we are projecting is the distribution of the sample axis within the crystal system. So like X axis is, well, it's about 1, yeah, isotropic. Y axis, that it's also not very deviating from the, isotropic. But the z-axis has very strong distribution in the crystal reference system. There is a high peak at 0, 0, 1. Means that the crystals are oriented so that the 0, 0, 1 direction is parallel to the z direction. So we have our bar, and this is the z-axis of the bar, and the crystals are oriented with their 0, 0, 1 axis parallel to that z-axis. Is it clear? There is a little bit of intensity also on 1, 1, 1, because the blue is almost 2. So there is some 1, 1, 1, but much less. The main component is 1, 0, 0. So now we know the texture. This is the initial one. So it must have been a bar from the symmetry, from the distribution. Anyway, we should know we had the sample and we were doing tensor testing on it. But from the texture, actually, without seeing the sample, I can tell you this was a bar. That's for sure. It was a round bar. So then, in what direction you are going to pull your bar? Of course, in direction Z, because this is the longitudinal direction, this is the axis of symmetry of the distribution itself. So we should then make a tensor testing that certainly if you want to be coherent with our reference system, in which axis? In direction Z. So yesterday, we were doing simulation on which axis? Which one? X, X1. So we are doing wrong. We have a bar, and our experiment was pulling perpendicular. And it doesn't make any sense, right? So that's why I'm telling how important to study the texture as well and just to be coherent. But it's interesting, we already published the paper, you know. So yesterday I sent a message to Sudeep. Sudeep, what happened here? And he said, oh, Professor, this is a mistake. Of course, we are doing some mistakes, but never mind. We can redo the simulation on the z-axis, right? So we only just go back. Mistakes are happening all the time. The more complex work you do, and it's becoming more and more complex. Science is getting so complicated that the probability of making mistake enormous. Luckily, we have time, and research needs a lot of time. That's why more and more time, because more and more mistakes we are doing. We are not doing this by purpose, but you see, it happens because it is really complex. We didn't think of very deeply. You are doing crystal plasticity, polycrystal plasticity. You have to verify everything. Anyway, so I just verified this one yesterday. And then I said to Sudeep, who is working right now in France, that this is a mistake. But anyway, the paper was about strain hardening simulation, the technique, and it was a very nice work anyway. You see, if you want to repeat the simulation, you can do it, but we are not going to do now. But going back to the software, since then I changed the things here, I believe, yeah. You see here it is. I already changed because I did a simulation for pulling it correctly along the z-axis. Oh yeah, this is negative. Oh, no. More complex because you see it's even hexagonal now here, so now. So yes, you are right. Okay, so let's do the tension. Let's do the tension. So minus 0.5 is in both x and y axis, and this is positive, right? And we are going to do like 32 steps. I think it was 32. It was here 0.6, or actually 0.7 was used by Sudeep. Hardening is Bronkhorst hardening. Okay, we have a symmetry. Crystal symmetry is cubic, so it is a 0. Here we have hardening parameters, which I don't remember, but perhaps one of you was working out nice parameters. Do you remember? You know, tau sat.
The tau saturation will be 142.5.
142.15.
142.5.
And
X naught will be
296. And the exponent?
It will be 1.035.
Yeah. Okay. And then, yes, all these, right. But we were doing cubic. since then I installed here the hexagonal. I wanted to show you, later I will show you how to do the hexagonal simulation, you know. But I'm going to put back, oh, here it is. I left it at the end of the file, so I can put it in here, just replace. Yeah, this is it. No. Okay. I think it's fine now. So we are pulling direction Z, crystal symmetry, cubic, hardening parameters are there, and shape parameter. Actually, Sudeep neglected the shape changes for the tensile testing. He was putting 0, relatively small strain, 0.3. There is not much shape change, but we had better consider the shape change. It is certainly better. So this now, end of slip systems, you know, then it's finishing here. The rest is not read by the software. And now we can actually repeat the simulation. Let's do it. You still remember how to do it? I hope so. So, you know, I'm making my DOS window. Here is my DOS window. I go to my directory and I type SC, self-consistent modeling. Very fast. We are getting the result in a short time. And if you look, have a look at now the texture we obtain. Is there any texture evolution during this 30% tensile deformation? It's not complicated to check because the output file of the simulation is called temp SMT, this one. So it contains the list of the orientations, which were initial one, now in a new position, now in the after deformation. And we can just, you know, easily plot it with the ATEX software. So I'm going to the ATEX software, the option of importing data by orientation list, and I choose the temp SMT file, which is the simulation result. I do not need to change anything in the parameters, just create the suitable file and then open it. And now let's look at the texture and pole figures first. You know, this kind of software, what you see here, this beautiful software, did not exist before. Like I was doing texture simulation already 40 years ago. There was nothing, no whatsoever. So I had to make the whole process, you know, to create the pole figures, to create the ODFs, without any existing software. Now you are in much better situation, you know. So I also enjoy the new situation, but there was nothing. So here you see it's actually different, much better defined, yeah? More circular, intensity is changed, like the 100, intensity was 4.5, and now it is 8.21, you see? So it became, the texture became more pronounced, sharper. And you see in the middle, we have the 100 peak, And then another circle, this is also 100 orientations. But it belongs to actually another so-called fiber texture. And then, of course, at the periphery, we have the third 100. There is only 3 100 direction in the crystal, you know. So we can have 3 circles. 110, there is more, but they almost coincide here. And 111, we can distinguish finally on the figure only 2. This is common, and in here there are some more. But it is more clearer if we look at now, instead of the pole figure, look at the inverse pole figure. You see, beautiful. It's really wonderful. Because, well, as you can see, X and Y, there is no specific component in it. A little bit of 101, but not significant. But the big change which happened now during the tensile testing, that here we had already initially a 001 component. And we identified a small 111 component, but now you see the 111 is strong. So we were pulling only 0.3 strain on the sample. And we got a strong 101 component, and the 100 remained. Actually, they were all existing before, just now the proportion changed. And even such a relatively small strain in terms of, you know, large strain, it is not big, significant texture evolution can happen. This is FCC material. Here the texture changes are visible easily, but in hexagonal, if there is twinning, it's even more spectacular. It can be very spectacular. Small strain and completely different texture. So that kind of calculation I would like also a simulation to do with you, so that you are a little bit see what other possibilities, what are further possibilities in terms of simulation work. Any question on this part? Perhaps I want to show you the, I close this one. I want to show you the hardening function, because I was repeating the experiment, the hardening simulation work. I repeated, yeah, this is what I got here. Pulling in the right direction. So the procedure which I was doing led at this difference between the experiment and the simulation, using the initial guess of this empirical fitting. This is actually already very good. And now only by changing the tau sat value, actually one can make it perfectly coinciding. So it's also possible to do, but the coefficients are slightly changed because actually we are now pulling in another direction. There is another population of orientational grains. But it's working, the process is working equally, very good. In the future, you can also do, you know, easily simulation work of this kind, and I hope that you will be able to produce such high-quality simulation work, at least for the hardening. And once the hardening is identified with these 4 parameters only, then any other polycrystal plasticity simulation can be done for your purposes. So, what I want to show you here is now going to hexagonal case. In hexagonal, already the crystal structure, the crystal symmetry is different. We need 4 indices to describe crystallographic directions. Let me open this control file. So the very same program what we use for cubic simulation can be used. Self-consistent code is very general. It is set up also for the hexagonal simulation work. So let's do some compression on the same kind of distribution. This is just for an example, what we did for the cubic. So imagine we have a bar in which there is not a hexagonal texture. It's such that most of the grains are with the 0, 0, 1 axis, means the z-axis or c-axis of the hexagons are parallel to the bar. And we are going to compress this one. And imagine a magnesium material and see what is happening when we use the suitable slip systems and also the suitable possible twinning systems. So we do simulation hexagonal. I said main difference is that here this so-called tuning parameter of the interaction law in the self-consistent modeling is different for the hexagonal. It was about 0.6, 0.7 for the cubic one and only about 0.1 for the hexagonal. This represents a smaller value of interaction parameter, represents more heterogeneity in the modeling. Heterogeneity in terms of mostly strain, but not in terms of stressed local stresses, but for strain. Okay, so grain shape, let's make it equiaxed. Constant strain path, let's do about the same strain. And we are going to do compression because I know that if you want to see some twinning in magnesium, we better compress it, not pull it, because then the so-called tensile twins, they are called tensile twins, they are activated in compression, but not in tension. So this is the opposite. Our deformation tensor is like this. We are going to choose the hexagonal one. I copy it, the file which is already prepared. Where is it? This one here. No. Is this one? No. Do I have it? Oh, of course. Here it is, yeah. I just don't want to lose the previous one. No, I'm not losing. Okay. I can delete. Here we have to make it hexagonal. Option 1. And of course now the hardening parameters are different. The hardening parameters. Let me take the hardening parameters from a real nice simulation work done by also Sudeep. I will find it. I have to go in my computer. Here it is. to see what parameters he had. Is that possible? I hope so. Okay. Yes, so I hope these are the right parameters for hardening. Okay. And then let's see for the slip systems. In hexagonal, it's completely different. We can distinguish the so-called basal slip, and there are 3 slip systems in the basal slip. They are here. You see, 3 of them, and we imposed 27 megapascal strength to the slip systems. The prismatic ones, they are also 3. That follows here. Well, they are made more difficult, 52, because actually magnesium is deforming the most easily on the basal planes. So we make the prismatic planes more, prismatic slips and direction dislocations more difficult. And then there is a pyramidal C+A type slip in hexagonal. There are 12 such slip systems are existing, and we make even more difficult, 78 megapascal. So there are 3 different kind of slip system families which are used in the simulation. We specified that the C/A ratio has to be 1:6 to 4. That's for magnesium. We specified also here that total number of slip systems is going to be 30, which includes sorry? Pyramidal, just pyramidal C+A is taken here. Now, you would take pyramidal A slip? This is pyramidal C+A, yeah. This is the plane, the slip plane, which is like you see oriented. It has an axis, one here, and this is the direction. So the first one is the plane, and the second one is the direction. Now, there is also 2 twinning families included. There is the tensile twins, which can be 6 different kinds. Here they are. And for completeness, the third Miller indices here, Miller-Brother, more exactly. And they specify the rotation axis for the twins. Twin can be considered as there is a 180 degrees rotation around the specific axis, which makes the crystal lattice into twin orientation. So this is given in order to make the twinning in the code to make it. Because I have to explain to you how this twinning simulation, is imagined and done in the polycrystal code. So there are tensile twins, and there are also 6 compression twins, which are considered. It's important that we have to specify how much is the shear strain which is associated with the creation of twins. Twin is such that, you know certainly a lot of things about materials and crystallography. A specific exact value of shear is needed in a specific direction, and then a given volume of the matrix is switching into the twin position. The same material, individual atoms do not move much, basically, but it's a kind of macroscopic shear, and a whole volume is switching. So this is, if everything is fine, specifying all what is needed, but we shouldn't forget about these 2 parameters here. This is the amount of shear in the family for twinning. We have 5 families here. The first 3 is not twinning family, it's slip. So then the shear strain for twinning is 0. This is how the code knows this is not twinning. But for twinning, there is finite shear strain on the shear planes, on the twinning planes, and for the tensile twin is this much. It's quite small. You see, only 0.131 local shear is sufficient to switch the matrix into almost 90-degree rotated version, because that small amount of shear strain locally, crystallographically, will, in tensile twins, is going to change the orientation of the matrix almost 90 degrees. It is enormous. This is why I said that spectacular orientation changes and texture variations can happen in hexagonal deformation. And the second value is for the compression twin shear strain. So all this, if it is all this is well defined, then the code will do now the simulation work for hexagonal case. Make it sure that it is right. And the window is still open. You just have to type SC and push the button and pray. Not even need to pray. It's working. Looks to be the same thing, but this is not hexagonal. A little bit slower, yeah, than the FCC. Here we go. Now, what we can do now here is to look into was there any twinning activity? And sleep is for sure. Sleep is making mostly the plastic deformation, but was there any twinning activity? For this purpose, we look into some kind of output listing files which contain information on what was the taking place, in terms of sleep deformation, twinning in our simulation. The first file here, which is called average stress dot or something, contains a lot of information. Increment by increment, one after the other increment. So you see first here there is a kind of input I step number 1, yeah, and then there are, it says increment, von Mises string 0, equivalent stress 66, and there is mu value, and then there is a E value. We don't need them. And then the next one is active systems. How many sleep systems were active? It says 3.08. Right. It's not 3, but it's an average value on many grains. So there was only about 3 in average sleep systems operating. You might ask how then the crystals could be deformed only by 3. But you see, we set actually this alpha tuning parameter very low. And if you would go to 0, you would end up with the static state. There would be only 1, probably sleep system activated for the non-symmetric orientations. Only 1.
Also, I think students, they would have the sleep system corresponding to this in this SC file.
You don't have it. Oh yes. You would like to do the simulation? Yeah. Okay. Well, let me. How can we do that? You only need the control file. Yeah, the SC control file. Okay, so I will put it into. I have to go to, Google Drive. Okay, and here I can add so the SC control file, this one here is still the cubic one. If I replace, you will lose this one. Email? Oh, I send it to you by email. Okay. Okay, so now you have it. I mean, you can send it. this file is coming. Actually, it also contains, at the end, the FCC. So you don't really lose it, even if you replace. Because only this part, the slip systems and this has to be replaced, and then also for cubic. So you only replace the SC control file, and then you run the code. Then it's doing the hexagonal. Oh no, if you look at the result, it's very varying. Like in the first step, there is an average number of slip systems, only 3. Okay? Twinned volume fraction, 0.06. There is already twinning. Already in this small step, 6% twinning is there. 6%. And then number of reorientation, this is the next parameter here, 0. I have to explain you how this code is handling twinning. There is not yet actually made a new, none of the volume of the material is switched into the twin position. But the volume is already counted, because this code here is using a very specific twinning simulation technique. It's extremely difficult to simulate twinning because of the orientation, sudden orientation change. You have to put a certain volume of your grain into twin position. It's like having a new grain within your original grain. And there are many variants. So, number of variants here can be 12 different twins. So, and those orientations, they are not created. So what the code is doing here, and that was the invention of Paul van Houten and Carlos Tomé, who were proposing that let's just watch how much would be the volume of twin to make the twin orientations. But we are not going to make all the twins. We are watching for that variant which has the highest activity. And if it reaches a certain volume, the volume is counted, but the orientation is not created, How much volume is corresponding to that increments of deformation in terms of twinning is counted, but the orientation is not made. After a certain high volume fraction for a given grain, then the code will decide, now it is big enough, and now I replace the initial grain completely with one single twin variant. That's the most activated one. The predominant twin reorientation. It is called a PTR scheme, was proposed by Carlos Tomé 30 years ago. And then only one variant. So then the number of grains is not changing in the simulation. But certain grains, at a given moment, they switch into twin. You must have a very large number of orientations, because this, in a statistical manner, if we examine twinning, this is quite correct, just for texture change evolution, and even for strain hardening also. It is quite okay. The simulation is working quite well with respect to the experiments. But in terms of micromechanisms which is happening in the material, is totally wrong. But finally, the texture will be okay. So since then, there is a new approach which was first proposed by Khalidindi in 1998, and but was not used for simulation purposes. Surya himself, he did not use it really. It was kind of introduced by himself. It was a very good initiative, but not used. So later on, I was taking his idea and implementing it into the simulation, into the self-consistent simulation. And then it is really physically a very correct twinning scheme. So there are a number of papers on it now, and it's called now the all-twinning approach. All-twinning approach. Meaning that we create all the twinning variants already before the simulation starts. So that there is one mother grain with the volume, and like if there is 6 tensile twins, then 6 satellite grains are created with 0 volume fraction, but their orientation is made. And then we are putting volumes progressively into each variant in each increment of the calculation. And then their volume is increasing, and they are part of the polycrystal. So certain variants which are active, those grains will increase in volume, and they are there. There is no any artificial switching of one grain replacing suddenly at a given strain with one variant, you know. No such a thing. All.
You like which variant is activated in higher fraction? How is that decided?
How do you quantify that? Oh, that's the basis of. I have to explain that. Yeah, I know. Perhaps after the break, I'm going to explain that. Okay, that's not too complex. Yeah, I will. And that so-called all-twinning variant approach is extremely successful. So much that the texture predictions are in extreme quality. They are coming, and even individual grain, initial grains, their activity, how they are twinning, which variants appear, with what volume, they could even be predicted with the VPSC. So that we did not expect. This work, the most complete work was done also with Sudeep Sahu, with him. He was very enthusiastic about it and succeeded to make extremely nice modeling. A beautiful paper in International Journal of Plasticity is published on that. And you should look into that. It's enjoyable to read how, with what precision the simulation could reproduce not only, the texture itself, not only the strain hardening curve, but also the general volume fractions and individual volume fractions and individual variants in but 100 grains which were studied individually also in the magnesium compression testing. Beautiful work. So that kind of approach was put into another code. I'm not using that code here because it is so complex that I would need too much time to explain how to use it. So that really needs somebody who is dedicated and choosing that research field to produce more accurate and more, powerful simulation work for twinning. There is not much, not enough yet done with this modeling, but the old twinning variant approach was used also for trip steel, where it was also successful, and then for magnesium, and now it is being used for titanium with another colleague who is with me from Kharagpur, Devesh. He's doing for titanium with double twinning, so that in his material, first there is tensile twinning, and then within the tensile twins appear the compression twins. Then it's another complexity. It becomes horribly complex, but the code is working. And once you make the code, you only do it once. After it can be used for many different purposes. So he's right now producing results on that for titanium. So if you got the SC control file, did you get it? No? Yes, because you say yes. Yeah. Then just run it. Just run, and then you get the hexagonal texture and all the results which are here. So let's go into the results. Here you see this is just one increment. All this block is result on one increment. And all averages here, averages. So you see what is the stress tensor on the sample. You see? The main component is the compression stress. There is also stresses in the perpendicular directions. They are about equal. But this is deviatoric stress. The true stress would be here 0 and 0 also here if we add the hydrostatic stress, which is always there. You see the shear stress components are small with respect to the main compression, because we have quite a symmetric and standard deviation in stress. It is actually with respect to, I think, 1, yeah? No. It's how much is the variation of the stress components from one grain to the other. Strain tensor, but of course it is what we wanted to impose. There's a little bit of deviation here from -1. The self-consistent code needs a certain precision at macroscopic level. So this is just a small deviation from that. It has to stop at a given precision, But this is good enough. The standard deviation in strain, you see it is much higher than in stress. We have such a situation when the stress state is quite homogeneous in the material, but the local strain is very different. So going to the second step, we will have here, so increment 2, we have still 3 slip systems about active. Volume fraction of twin is 13%. No reorientation yet, so there is any grain was not switched into twin position. And these here, for the families, so there are 5 families. The first 3 is slip, yeah? Basal, prismatic, pyramidal, tensile twin, compression twin. This represents here the total is equal to 1. The relative activities of these 5 different systems. You see the high activity in tensile twinning, no activity in compression twin. Going further, because you are interested, here step number 3. Step 3, still 3 slip systems. Almost 20% of volume fraction in supposed to be in twin position. 245 initial grains were switched now into twin. It was 0 previously. You know, the code is working in such a way that deciding that, well, in this grain there's a lot of activity, too much. I will replace it with its most active twin variant. There was 254 situations happening in that increment. And here you see the activities of the 3 slip systems. There is a little bit of pyramidal, and still there is no compression. So this is how it continues. By the very end, so here 32 steps. Here we are. We have 3.35 average number of slip systems active. Twin volume fraction 17.7. How come it was already 20% before? Perhaps it was only in this increment. Now it's too much. It is true that the code doesn't. The code. Oh yeah. Well, I don't have an answer, but 368 reorientations happened in twin position, and these are the activities. Right. In the meantime, your simulation was running. You can have a look at the same file, but this is a possible analysis, and then one can dig out, these data and making a plot. Also for the stress strain behavior, we have a file which is called, this so-called hard dot file, von Mises strain, von Mises stress, work equivalent stress, Taylor factor, and then here the stress components, how much in average, dislocation density is no, and all this, this is not 0 because we are not using that hardening dislocation cell-based hardening rule. And what we are going to see after, but perhaps we make a small break, yeah? We do? Is the texture. What kind of texture developed due to, twinning, especially. Do we have a break? Yeah? It's okay to do it now? Good. After we look into the texture.
So in these examples, we are not separating the